I couldn't quite let go of that last problem, the one about the record in the mile run. And I went to Wikipedia, and I took all the records since 1913. And that's when a international sanctioning body for track and field was formed, I think in 1912. And so I thought that would be a good place to start. And the record was broken about 31 times. The last time was in 1999. Now the textbook, the last time was 1993. Since then, one other guy broke the record. So I plugged in, I calculated my own regression line. It was a little bit different from the textbook because he used a little bit different data than I did. And the data looks, let's say it looks kind of like this. Now I've exaggerated a little bit. It looks fairly flat, but there's a slight curve to it. And so the regression line, what it does is it connects the dots in a straight line. It doesn't connect the dots in a straight line, but the regression line is the line that best fits the dots. It's the best average. So that's the regression line. But there's, I believe, with good justification, that there's a better fit to this. And let's see, let's do this in green. A better fit is a exponential decay. It's a regression function. In other words, theoretically, we should be able to fit these points, scatter plot points, to this curve. And this curve, which is an exponential decay, what happens, an exponential decay decreases like so, then eventually it gets closer and closer to a theoretical limit. It doesn't ever quite touch. And so we call this the asymptote. It's asymptotically approaching this line. And so as I discussed in the last video, the regression line will just keep on going. And eventually, somewhere a couple thousand years out in the future, someone theoretically will be able to run the mile in 0 seconds, which is clearly impossible. And so my point on this is that when you look in a fairly short time frame, when you look in a fairly short time frame, data can look rather straight. And in that case, a regression line fits it very well. But as you extend that time frame out, it may not ultimately be linear. It may not be a straight line. It may be, for example, in this case, you expect an exponential decay. In other words, it's going to be harder and harder and harder for someone to break the record in the mile run. And eventually there's some limit out there, which is the theoretical limit of the human body. So I wanted to bring all of this up to show you some shortcomings with linear regression. It's very good in the short term because data tends to look, in many cases, straight line. Just like standing here, going out in the front yard and looking around, looks like the Earth is flat, right? Doesn't the Earth look flat to you? That's because the Earth is so large on the scale, we don't see that the Earth is curved very easily. And similarly, when data is compressed together, it may appear straight line flat, when in fact, if you were to stretch it out over a longer period of time, it may be some kind of curve to it. And that has to be the case in the mile run. So, what did I try to do about all this? Well, I tried to fit this function to it. And I don't expect you to know this, but if you've had some more advanced math, the function I tried to fit was y equals to a plus b e to the cx. And e is the exponential base, and if you don't know anything about this, then don't worry about it. But if you've seen exponential functions before, this might make a little bit of sense to you. I tried to fit the points to this function and ran into very serious mathematical hurdles. I think it's algebraically impossible to do that. Okay, so I tried some various tricks and techniques I thought up, and could not get a very good fit for this. So I've given up on that for the moment, at least. I'm not sure it can be done very well. And certainly after beating my brains on it, I couldn't get it done. So I'll don't worry about that another day. So there you go. There was a problem in itself. Well, how do you, if you think this green curve is a better fit, then how do you fit the points to it? And at the moment, I'm not sure there's a good way to do that. I'm not sure there is a way to do that for various reasons. Well, so here's what I ended up doing. I took the last 3 years. I'm sorry, the last 3 records. And they're as follows. In 1985, someone ran the mile in 3 minutes, 46.32 seconds. In 1993, Morcelli, who's mentioned in your textbook, ran the mile in 3 minutes, 44.39 seconds. In 1999, a Moroccan named Garouge ran in 3 minutes, 43.13 seconds. So I made an assumption that these guys are as representative as anything for the mile run. So using just 3 points on the graph, representing the last 3 records, I did connect it with that exponential decay. That's very possible, actually, when you only have 3 points. Just when you have more than 3 and want to do a regression line, you run into problems. So I did come up with a function that fits this, and my goal was to figure out, well, what is that theoretical limit of the human body? You know, what's the prediction for the best time anyone could ever run the mile? At least based on our current understanding of physiology and athletic training. What's the very best a human could do in running the mile run? And my estimate is 3 minutes, 33.12 seconds based upon this, just using this data here. So I'm guessing that we can shave another 10 seconds off the mile run. It may take an awfully long time, could take a century or 2, but that we can get it close to 3 minutes, 33 seconds. So, do I really believe that? I think it's in the ballpark. I really do. I think it's a good estimate. Is it precise? I would say no. And no, because there's still variability in our sampling. As long as there's some variation or sampling due to all the statistical factors that add randomness into it, then we're not going to get a precise definitive answer on what's the very shortest someone can run the mile. So, but this is my best shot at it, and thought I would share that with you.